So for today, we're going to get the value of the cosine bt in time function, or rather we're going to get the equivalent of this time function into the complex frequency function using the Laplace transform. So the Laplace of cosine bt dt is equivalent to the integral of e raised to negative st cosine bt dt approaching from 0 to infinity. So as you can see, this expression or this equation can be solved using the integration by parts. So for our u is equivalent to the cosine bt, and the derivative of u is equivalent to the negative b sine bt dt. So dv is equivalent to the e raised to negative st dt. So for us to get the value of b, we have to integrate this, so we could come up with this b is equal to negative 1 over s multiplied by e raised to negative st. So plugging in the solution of, or in the equation of the integration by parts, which is uv minus integral of v du. So negative cosine bt multiplied by e raised to negative st over s approaching from 0 to infinity minus the integral of negative 1 over s times negative b sine bt multiplied by e raised to negative st dt. So substitute or rather evaluating these expressions or plugging in the limits, we could come up with 0 minus to the negative 1 over s. So negative times the negative is equal to the positive, so this will be 1 over s minus the b over s, which we factor out the constants b over s. So negative b over s multiplied by the integral of e raised to negative st sine bt dt approaching 0 to infinity. So another integration by parts. So let our u with b sine bt du is equivalent to the b cosine bt dt dv, okay, from the first equation, which is equal to e raised to negative st dt, and the v is equal to negative 1 over s multiplied by e raised to negative st dt. So plugging again these values in the equation of the integration by parts, we come up with, bring down this 1 over s here, from here the 1 over s here, so minus bs, also the bs, multiplied by the negative sine bt e raised to negative st over s squared plus b over s multiplied by integration of e raised to negative st cosine bt dt. So again, now we can see that this integration has occurred from the first expression or equation. So we can let this one with the y, and so could come up as y is equal to 1 over s plus distribute this one, so it would be b sine bt e raised to negative st over s squared minus b squared over s squared y, which e raised to negative st cosine bt let be y. So transposing this one, y plus b squared over s squared multiplied by y is equal to the 1 over s plus b sine bt e raised to negative s t approaching over s approaching from 0 to infinity. So plugging this limits would come up to this one would be equal to 0, so the remaining would be the 1 over s. So we can get this one by getting the LCD, or least common denominator, which is the s squared. So, and also we factored out the y so that we can separate this expression from this variable. So we can transpose this one, so we can get y is equal to 1 over s multiplied by, if you're transposing like this, get the reciprocal of this one for us. If you are transposing a expression like this, so this would be equal to s squared over s squared plus b squared. So multiplied by this one's cancel, so y is equal to the s over x squared plus b squared. Or rather, the Laplace of cosine, rather, the Laplace of cosine bt is equal to the s over s squared plus b squared of the complex frequency function.